Hi everyone, welcome back to Math 261. This is Scott. Let's get started. What we're going to be doing now is looking at the specific case where we have a matrix whose eigenvalues are not real but are complex. So, complex eigenvalues. So here's the setup. And we're really going to be focused primarily on 2 by 2. So A is a 2 by 2 matrix whose characteristic polynomial has complex roots. Alright, so first off, what we can do is we can find the eigenvalues using, for example, the quadratic formula. Then, for each eigenvalue, we can find the corresponding eigenvectors. So, note, for each complex eigenvalue, we can find a complex eigenvector. So this is V, which is going to belong to not R2, but C2. So these are this is the vector space of two entry vectors each of whose entries is a complex number. So two entry complex valued vectors. Okay, so here's how this will go. And it's easiest to see with an example. Alright, so let's say that A is equal to -1, -1, 5, -5. And what we're going to do is find the complex eigenvalues and a basis for each of the corresponding eigenspaces. Alright, so we start this the same way we would start any other eigenproblem. We don't know, just looking at this, what kind of eigenvalues it has. And so we set up the A minus lambda I, which means, of course, subtracting lambda along the main diagonal. But then it is the determinant of this that we are after. And we have to set that equal to 0. That is now the characteristic equation. And we will just see where this leads us. So negative 1 minus lambda times negative 5 minus lambda plus 5 equals 0. And then this is going to be a lambda squared. It's going to be plus 5 plus 1. So it's plus 6 lambda. And then over here, we're going to have plus 5 plus 5 is 10 equals 0. Now, those of you who are adept at algebraic arts, such as completing the square, have a way of doing this that could be very convenient and easy. However, if we don't know anything about that, we can always just go to our old reliable quadratic formula, and that's going to give us then lambda is equal to negative b is negative 6 plus minus square root b squared minus 4ac divided by 2a. It's going to be so negative 6 plus or minus, and here we're going to have square root of negative 4 over 2. It's going to be negative 6 plus or minus 2i divided by 2. Which is going to be, then I can divide both of these by 2, and it's going to be negative 3 plus or minus I. So what we have are two eigenvalues. One is negative 3 plus I. The other is negative 3 minus I. Whenever you have complex eigenvalues, they will come in these, which are called conjugate pairs. And the difference between them is just that where one has a plus, one has a minus. That's the meaning of the word conjugate in math. So complex solutions will always come in conjugate pairs. Now, to find the eigenvectors, here's the trick. So finding eigenvectors. So here the key is if we just take the matrix A minus lambda I. So we set this up, and then we augment it with the 0 column. So if we take this, then we can choose either of the rows to use, and we will not do the row reduction that we typically do because it's a little bit too complicated here. So we don't have to row reduce. Just swap coefficients. I'll show you what that means. So for the example, we'll start with lambda equals negative 3 plus I. So lambda equals negative 3 plus I will be our first one. And so A minus lambda I is going to equal, so it's negative 1 minus negative 3 plus I, and negative 1, and then 5, and then negative 5 minus negative 3 plus I, and then you would just do a little bit of routine algebra here. So we could just write this as -1 plus or minus negative. So it's going to be plus 2 minus I, -1, 5, and then so it's -5 minus -3. It's going to be minus 2 minus I. And now what we can do is we can just arbitrarily choose either of these that we want. And I think by default your book, which means also your online homework, by default just chooses the second row. So we'll choose this. So then I guess I should augment this with zeros. So augment it with zeros. Augment it with zeros. And so what we're going to have is 5x1 minus 2 minus I, guess plus -2 minus I x2 equals 0. And so then what that means is 5x1, if I add this to both sides, it's going to equal 2 plus I times x2. And then if I just swap the coefficients, I can just take x1 equals 2 plus I, and x2 equals 5. So then that gives me an eigenvector of 2 plus I and 5. And now I can repeat the process for the other one, lambda equals -3 minus I. And then when we get to the end, we can compare what we got with what we had before. So now a minus lambda I, augment 0, and so what we'll have here is -1 minus -3 minus I, -1, 5, -5 minus -3 minus I, 0, 0. And then this will equal, so it's going to be 2 plus I, -1, 5, and then -2 plus I. And if I, again, just choose the second one, just because I think that's the default that your book opts for, we could just as easily choose the first one if we wanted. That's going to mean 5 times x2 plus -2 plus I, sorry, 5 times x1 plus -2 times xi plus I times x2 equals 0. Move everything to the other side, so 5x1 is equal to 2 minus I x2, which gives us x1 equals 2 minus I, x2 equals 5, and so that gives us a new eigenvector of v, which equals 2 minus I and then 5. note here, the eigenvalues come in conjugate pairs. Lambda equals A plus and minus BI. The corresponding eigenvectors are also conjugate. And actually, you should say complex conjugates. And what that means, so complex conjugate, that refers to changing the coefficient of the imaginary part, changing the coefficient of the I from positive to negative. So switched signs on the I terms. So that's what it means to be a complex conjugate, is that what's called the imaginary part, the part that has the I, that becomes the opposite of what it was. Now, there's a special form for these complex eigenvalues. So these are matrices that look like this. So special form A, B, minus B, A. So this is a special form of a complex eigenvector. Of a case of a complex eigenvector or eigenvalue. And this is a special situation that is closest to diagonal, but for these particular kinds of matrices. So this is the closest analog to a diagonal matrix. Now, observe that if we were to take a matrix like this, it bears a very striking resemblance to the matrix for a rotation. So let's recall how that goes. So recall, I'll call it R for rotation. R equals, and it goes cosine phi, sine phi, minus sine phi, cosine phi. So this is the same as so this is the matrix that accomplishes a rotation by an angle of phi in R2. So this performs a counterclockwise rotation by phi radians in R2. Now this and this have a certain very, very close similarity to each other. The difference is, though, that these are automatically going to have a certain Pythagorean relationship with each other. Namely, this squared plus this squared has to equal 1 in order for these to correspond to the angles on a unit circle. So a squared plus b squared may or may not equal 1, just according to this special form, but we would like them to. So here's how we scale it in order to make this have the same form. So for a, so back to a, so if a is equal to a, b minus b, and a, then we want to scale it in order to make the entries satisfy Pythagorean identities. So scale the matrix by r, which is going to equal the square root of a squared plus b squared. So then a is equal to, so basically pull out the r, so that we can have a over r, b over r, minus b over r, and minus a over r. But then we can rewrite this as r times the identity. So a over r, b over r, minus b over r, and a over r. And this part accomplishes a scaling and this part accomplishes a rotation. Now, the angle of the rotation that's being accomplished here will be the angle that corresponds with this point on the unit circle. Now, the easiest way of untangling what that must be is to use an inverse. In this case, tangent would be the easiest. So to find phi, the easiest thing is to recall that AB is where the image of E1 would be. And that's equal to angle phi. Now, if you remember your trigonometry, the easiest way in a case like this to find the angle phi given something like this would be that phi, the tangent of phi, is equal to b over a. Now, the problem with this is that if we're assuming that the scaling is always going to be by a positive amount, not a negative amount, then we may have to make an adjustment to the inverse tangent in order to get it to the right quadrant. So phi is equal to the inverse tangent, or arctan, of b over a, or possibly it's equal to inverse tangent of b over a plus pi. This is if AB this is if AB is in quadrants 1 or 4. And this is if AB is in quadrants 2 or 3. And the reason for this necessary adjustment is that if you take the points that are diametrically opposite to each other on the xy plane, their negatives will cancel each other out, and it'll be the same ratio, b over a, as the ones with the positive ratio. And so we have no way of telling without looking at it if b over a, if that's the ratio that represents being in quadrant 1 or 4, or the diametrically opposed quadrants of 3 or 2. But this is how we find the r and the v. And a note, in your textbook at least, it wants you to find the phi that is specifically between negative pi and pi. So the textbook wants phi that's in between negative pi and positive pi. So add or subtract. Multiples of 2 pi to put it in that range. Okay, so let's try an example, and the example would just be find the r and the phi. So I'll just put it like that, and the A will be a matrix. It'll have this form: square root of 3, 3, negative 3, square root of 3. All right. Well, r is equal to the square root of a squared plus b squared. So that's going to be the square root of 3 plus 9, which is going to be the square root of 12, which you can also, if you want, rewrite it. So this is 4 times 3, pull out a perfect square, and get 2 root 3. So r equals 2 root 3. Okay, so be it. So then if I pull out 2 root 3 from this, then I'll get a equals 2 root 3, 0, 0, 2 root 3. And then times right here. So I'm dividing by 2 root 3, so it'll make a 1/2. And I'm dividing by 2 root 3, and that's going to make a root 3 over 2. And I'm dividing by the root 3, 2 root 3, so it's going to be making a negative root 3 over 2. And then over here, that's going to be another 1/2. Now, 1/2 and root 3 over 2, these are actually familiar numbers to you as far as possible values on the unit circle. So you can actually perhaps even figure this out just by reasoning it out. So we've got negative, so we've got positive 1/2 and negative root 3 over 2. So clearly we're talking about the angle that is down there. And so you might actually already know that this is equal to negative pi over 3. But you don't need to know that because we can just say, well, so it's quadrant. Most important thing about it is that it's quadrant 4. So it's going to equal tangent inverse of b over a. So that's going to be negative 3 over root 3, which you don't have to be, so you don't have to be a hero, and you don't have to go figuring this out on all just using your brain. You can just use a calculator and have your calculator do the hard work for you. So if you have a TI-89, you can do a tangent inverse, and then it was negative 3 divided by the square root of 3, and a TI-89 would be perfectly capable of telling you that it's negative pi over 3. If you have a different kind of calculator, for example a TI-84, then you may want to have it set to degrees and then convert to radians, so that way you'll be more likely to be able to spot an exact answer. And if this number had come out not within the designated range of negative pi to pi, then I could add 2 pi or subtract 2 pi in order to put it into the designated range. I'm not sure exactly how much flexibility the online homework module will have on that, so I'm just in case, I want to make sure that that you know what you would do. Now let's go back to looking at the complex eigenvalues and eigenvectors, and I want to make a couple of observations. So complex vectors. So let's say that V, so if V is any 2-entry complex vector, so it's got two entries, each of which is a complex number, then the real part of V, which is how you pronounce that, this is the real vector that you get from the real parts of the entries. Of V, and then the imaginary part of V this is the vector you get from the imaginary parts of the entries of V. So in other words, the coefficients of I. So for example, let's say that V is equal to 2 minus I and then 3 plus 2I. Then the real part of V would be the 2 and the 3. And the imaginary part of v would be -1 and +2. So notice there are no i's written in this. So you don't write the I in the imaginary part. You're just making a regular looking vector. Okay, now this we introduced as a tool to the following, which is this is a theorem, and this is the complex eigenvalue equivalent of diagonalization. So this is the this is the analog to diagonalization. So let's say that A is a 2x2 matrix with complex eigenvalues lambda equals A plus or minus bi, and because we're saying complex, that means that I'm assuming that b is not equal to 0 here. So let's say that. Now take v to be an eigenvector of lambda equals A minus bi. So we're taking the negative one here. So minus bi. All right, then set p equal to the real part of v, and then the imaginary part of v. And what that will then give us is A will equal P, C, P inverse, where C has the form AB minus BA. So in other words, this is like the closest thing to being a diagonal matrix you can have if you have complex eigenvalues, and so this is the closest thing to diagonalization. And what this basically means then is that the effect of any matrix which has a complex eigenvalues, the effect of any such matrix as a transformation is going to be somehow a change of basis. The P and the P inverse do that. And then also a stretch by a factor of r, as well as a rotation by phi. So that's the effect, the geometric effect that complex eigenvalues will have, is they will always cause in R2 the effect of some kind of rotation, some kind of stretch, and that stretch will be uneven in the direction of the various eigenvectors. All right, now let's try an example, and here we're just going to be trying to find the P and the C. P and C as above. For the matrix A, which will equal -3 to -1, 5. Sorry, -5. Alright, well, we will start this the way we start all of our eigen things, which is by looking at the matrix A minus lambda I. And that's going to be a matter of subtracting lambdas along the main diagonal. So negative 3 minus lambda, negative 1, 2, minus 5 minus lambda. Now, in order to turn this into a characteristic equation, we need to take the determinant and set it equal to 0. So, what we've got is negative 3 minus lambda times negative 5 minus lambda plus 2 equals 0. So it's going to be a lambda squared, or what have we got here? We've got positive 3 plus positive 5 is going to be plus 8 lambda. Over here we got positive 15 plus 2 is going to be 17. It's equal to 0. And again, perhaps you know about completing squares and things like that to make this algebraically a little cleaner, but if you don't, no big deal, because the quadratic formula will be able to handle all such things. So A is 1, B is 8, C is 17, which means lambda equals negative B, so negative 8 plus minus square root B squared is 64 minus 4AC, so it's going to be 68 all divided by 2A. So we're going to have negative 8 plus minus, and here we can see already it's going to be negative 4, so it's going to get 2I all divided by 2, so it's going to make a negative 4 plus minus I. Now, the way we construct the proceedings on here is we take V specifically to be the negative one, remember, the negative one. So minus 4 minus I. There's an analogous theorem for if we had chosen the positive one, but it comes out cleaner if we take the negative one. So negative 4 minus I. So that is now the that's now the matrix, or sorry, the eigenvector that we'll be using. Sorry, that's the eigenvalue we'll be using. Eigenvector, to find that, what we need to do is look at A minus lambda I and put in this into that spot. So minus 3 minus negative 4 minus I minus 1, 2, negative 5 minus negative 4 minus I. And here, this is going to be just 1 plus I minus 1. 2 is going to be minus 1 plus I. And augmenting the zeros and whatnot, which we don't necessarily need to write if we don't want to, we can just automatically go ahead and work with this one. So 2x1 plus negative 1 plus I times x2 equals 0. These all go down the same path. So 2x1 equals 1 minus I x2, which means I can take an x1, which equals 1 minus I, and an x2, which equals 2. And I could have just as easily chosen it the other way, but I chose this, so that gives me a v, which equals 1 minus I and 2. Now the real part of v is then going to be 1, 2. The imaginary part of v is going to equal negative 1, 0, And here specifically, this means that A equals -4 and B equals 1, according to the A and B framework. So what that means is that P is going to equal 1, 2, -1, 0, and C is going to equal, so A is -4, B is 1, and then up here we'll have -B and A. Oops. And there we have it. Alright, so what this means then is that A could be rewritten as this times this times this inverse. And that's the closest thing in the case of complex eigenvalues we can have to a diagonalization. Alright, well that's going to just about cover section 5.5. Join me next time for another episode of Math 261. Until then, bye.